Hi, everybody. Welcome back to 5 Days to a Sixsky. My name is Mr. O'Sullivan, and we're ready for day 5, applications of the integral. So just like before, down in the description, you should find a link to the PDF that I'm going to be using here. So feel free to follow along. All right, here we go. So applications of the integral. One of the first main applications of the integral would be to solve differential equations, sometimes called finding a particular solution to a differential equation. Okay, so here we go. 5 steps that we need to keep in mind. First step, and the most important step, want to separate the variables. I'd start with the differentials, leave dy on one on the left side probably, move dx over the other side, and then just move the expressions for x and y to the correct side with the corresponding differential. So we separate the variables. And then second step, don't hate, we're going to integrate both sides of the equation. And don't forget, plus c is going to go on the x side or maybe the t side, whatever our independent variable is. Okay. And step 3, next thing we're going to do is we're going to sub in the initial condition, the IC, the initial condition. So they're going to give us some point, x equals something, y equals something. We're going to sub that in, and then we're going to solve for c, our constant of integration. Okay. Step 4, we're going to sub in the value of c into our equation. And then step 5, we're going to solve for y. Okay. We want to make sure if two solutions, we want to pick the equation or pick the solution that includes our initial condition. Okay. So in this case here, if we go back, the initial condition was x is 0, y is 2, and we get y is equal to plus or minus, square root or something like that. Then we need to take the positive root in order to be able to come up with a positive 2 for y. Okay. Another application of the integral to find the average value of f of x on the closed interval a to b. Okay. Well, if we're asked to find that, that is going to be given by the expression 1 over b minus a times the definite integral from a to b of f of x dx. That's going to give us the average value of f of x on that closed interval a to b. Okay. Again, I just want to point out, this is not the average rate of change of f of x on the closed interval a to b. That would be f at b minus f at a over b minus a. This is the average value of our function f of x on the closed interval a to b. Okay. Okay. Another application of the integral in particle motion. If we're looking for the change in position, also known as displacement, or particle's displacement, that's going to be given by the integral from some time, I'm going to say t equals a to t equals b, and we're going to integrate velocity with respect to time. That's going to give us the position at time b minus the position at time a. Okay. So that's the position of the particle at t equals b. That's the position of the particle at t equals a. And the difference is going to be the change in position or the displacement from t equals a to t equals b. Okay. If we're asked for the total distance that the particle travels, that's going to be given by the definite integral from a to b. And this time we're going to integrate speed, the absolute value of velocity. That's going to give us the total distance traveled by the particle from time A to time B. Okay. All right. All right. Other applications of the integral. Okay. Now we talk about area. All right. Well, area is going to be usually pretty cut and dry. That's going to be given by the integral. Surprise, surprise, right? We're doing applications of the integral. We're going to see the integral used here. So it's going to be the integral from some x value to another x value of our, let's say, some top or upper function minus another function, bottom function, the lower function. So f of x minus g of x. Okay. Or if we live in an alternate universe, sometimes they'll ask this, not as common, but if we could be looking at possibly in terms of y. So now we're looking at y equals, let's say, k, y equals L, and now we've got a function of y, h of y minus j of y. And our differential, of course, would be dy. In this case, this is going to be the rightmost function minus the left function, okay? A lot of times when we're dealing with these might be in a free response problem when we're looking for something where they say write but do not evaluate. So these are sometimes we see those wonderful words, write but do not evaluate. All we have to do is just come up with the definite integral. Okay. Okay, now we move on, add a dimension, and now we start talking about volumes of solids. Okay, there's two ways that we need to be able to find the volume of a solid. First is by forming a solid by rotating a region around a horizontal or a vertical line. And we want to remember in these cases, don't forget dessert, don't forget pi. Okay, so first off, if we have if it's rotate around a horizontal line. Okay. Everything's going to be in terms of x. Okay. The bounds, the integrand, the differential, all going to be in terms of x. Okay. Now what we have to do is say that does the region, does it border the AOR axis of rotation? So if the region borders the axis of rotation, we're going to have just one radius. If the region doesn't border the axis of rotation, then we're going to have two radii. Okay. So I'm going to say my axis of rotation, it's going to be horizontal line. I'm going to say it's going to be y equals k in both cases here. And I'm going to say that my axis of rotation is above, I'll say it's below my function. How's that? So for this case here where the region borders the axis of rotation, it's going to be pi. Get pi. And put pi right out in front like a constant, put out in front of the integral. So from some x to another x, and then it's basically just going to be the upper function, which I'm just going to say is f of x minus k, my axis of rotation. Don't forget that's a radius. I need to square it, and then dx. That's going to give me my volume. I can check there. I'm going to have three dimensions. I'm going to have 2 dimensions from that. I'm going to have 1 dimension given by the dx. So 3 dimensions, that makes sense for a volume of a solid. And if I have the region's dome order, the axis of rotation, I'm going to have the 2 radii. So I'm going to have pi, definite integral, a to b. I'm going to have my 1 radius. I'm going to say that's f of x minus k squared. It's going to be my longer one. Longer one has to come first, minus g of x minus k squared, and then dx. Okay. Could have the same thing next door in terms of y, and that's going to be if we are rotating around a vertical line. Could be the y-axis, could be another vertical line, x equals -2, what have you. Okay. But then everything, same kind of thing is going to happen. I'm just going to kind of do this. So it's going to be pi. These are going to be y values. I'll use a and b again, but y is a, y is b. And then my functions have to be in terms of y. So this would be f at y minus, if I use that same, in this case here, my vertical line, axis of rotation, I'm going to say is x equals k. You know what? I'm going to use c. I've just ingrained in my head that when I talk about a particular x value, I call it c. So I'm going to say c. So this would be f at y minus c. It's a radius, got to square it. dy, it's going to be right minus left. And then if the region doesn't border the axis of rotation, again, we got pi. We got y values for the bounds. And then we have 2 radii. F at y minus c squared minus g at y minus c squared. dy, respect that differential. Again, longer radius has to come first, followed by the shorter. And up here, this is going to be left. Oops, good catch there. Check that. How about right? Right minus left. You'll notice it's not going to really matter if we switch that order because we're going to be squaring that quantity, but I like to be consistent. Anyway, the main thing is, though, that the longer radius has to come first, and then we subtract the square of the shorter radius. If we don't do that, if we switch those, our answer is going to be negative. Okay, volume and area always positive. Okay, now moving on to the other way that we can form a solid, and that's where our solid, the region is the base of our solid, and the cross sections are going to be taken either perpendicular to the x-axis or the y-axis. And then we're going to have the cross sections are going to be known shapes: squares, rectangles, semicircles, equilateral triangles, or right isosceles triangles. Okay. Okay. So if cross sections are perpendicular to the x-axis, and this is the most common, okay, the entire integral, bounds, integrand, differential must be in terms of x. Okay. The cross sections are perpendicular to the y-axis. Okay, not as common. The entire integral, bounds, integrand, differential, etc., must be in terms of y. Okay, and again, these might be the case where it is right, but do not evaluate. Wibdani, right, but do not evaluate. We're going to love that because those, all we have to do is write the correct definite integral, move on with our lives. Okay. All right. So just kind of a quick setup and example here. So if our cross sections are perpendicular to the x-axis, again, that's the more common way that we'll expect to see it. It's going to be some constant. times the definite integral from a to b. And then it's basically just going to be the quantity f of x minus g of x, the top minus the bottom in our region, that quantity squared. Okay, and then dx. Same kind of thing if we do cross sections perpendicular to the y-axis. This is a little bit more rare. It's going to be a similar thing. It's going to be our bounds that are going to be y values. Our integrand is again going to be a difference squared, but this time it's going to be in terms, the functions are in terms of y, and it's going to be h at y, the right function minus the left function. Okay, again, the right and the left, since we're squaring it, it's not going to matter mathematically, but we just kind of like to maybe stay consistent with that. And then the differential is dy. Okay, now what changes here for each one of the different shapes is the constant that we have out front. Okay, so here we go. So if our shape is a square, the constant is a 1. Okay, we won't see it there, but if that's the case. If it's a rectangle with the width in the region and the length is 4 times the width, then the constant would be a 4, right? That's that 4 right there. If the cross section is a semicircle, constant is pi over 8. It's an equilateral triangle. It is root 3 over 4. If it is a right isosceles triangle, they're going to need to tell you, is it the leg or the hypotenuse in the region? If it's the leg, constant's going to be 1/2. And if it's the hypotenudal, the constant's going to be 1/4. Okay, so good idea to memorize those constants. Again, this is going to be pretty standard, the rest of the integral right here. Okay, pretty standard, either this one or this one. And then you just have to know, hey, what's the constant that I put out front? Okay. All right, let's do some problems. Okay, so if the average value of the function f on the closed interval from 2 to 4 is 3, and if f of x is greater than or equal to 0 for all x in the closed interval 2 to 4, what is the area of the region enclosed by the graph of y equals f of x, the lines x equals 2 and x equals 4 on the x-axis? Okay, well, we're talking about average value of our function. So we know that's going to be 1 over 4 minus 2 times the definite integral from 2 to 4 f of x dx. And they tell us that average value is 3. So that equals 3. Now they're asking, what is the area of the region enclosed by the graph of f of x, the lines x equals 2 and x equals 4, and the x-axis? Well, if we think about that, what they've just described to us, 2 to 4 f of x. Now here they did tell us f of x is positive, so it doesn't dip below the x-axis, but f of x is positive or equal to 0 on that interval. And so really what they're asking us for is, what is the area of this region right here? Well, golly gee, that's this definite integral right here. Okay, because that's f of x. Well, all we need to do, 1 over 4 minus 2, that's 1 over 2. We just need to solve for this. So I'm just going to multiply both sides by 2, cancels that, and we're saying that that is equal to 6. We're in the mix. That's our answer. I like it. Okay. All right. So a particle moves along the x-axis. Okay, the velocity of the particle at time t is given by v of t is equal to 4 over t cubed plus 1. If the position of the particle is x equals 1 when t equals 2, what's the position of the particle when t equals 4? Okay, this is a calculator problem. I can tell that it's question 78, so it's a calculator available problem. And what I'm going to do is I'm going to put v of t in my calculator as y1. But first, I'm going to do my setup. So what I'm looking for is, I'm looking for the position of the particle at t equals 4. Well, I know that's going to be the position of my particle at time 2. So I'm going to have 1 plus the definite integral. My bounds are going to be my times 2 to 4 v of t dt, and that is going to give me the position of the particle at time 4. This one right here, that's the position of the particle at time 2. So we can think of it this way. The position at t equals 2. What's this giving us? This is giving us the change in position from when to when? From lower bound t equals 2 to upper bound t equals 4. Well, that makes sense. The position at time 2 plus the change in position from 2 to 4 is going to give us the position at t equals 4. That's what we're asked to find. Okay, calculator time. So here we go. Let's see what we got in here. There's my velocity function, 4 over, obviously using x in place of t in my calculator, x cubed plus 1. So that is my velocity. So now I want to go, and I'm just going to put this in. Don't want to forget the 1. Pretty common mistake that students of lesser caliber than you guys might make. So 1 plus the definite integral, math 9, lower bound 2, upper bound 4. V of t is in my calculator as y1, dx, say a little prayer, and I got my position is 1.3525. Just practicing for my 4 places truncated for the free response. And please be an answer, please be an answer. Looks like my answer is C. Bada boom, bada bing. All right, all right. All right, particle motion. I like it. Application of the integral. Hey, look at this. Another particle. So particle moves along the x-axis. Again, position, particle motion in one dimension, moving horizontally along the x-axis, so that anytime t greater than or equal to 0, I just make a note of that, its acceleration is a of t is equal to negative 4 sine of 2t. If the velocity of the particle at t equals 0 is v at 0 equals 7, and its position at t equals 0 is x at 0 equals 0, then its position at time t is x at t equals. Okay, and that's what we got to figure out. Well, you can kind of think of it like this. We're given the acceleration function, and we've got to get to the position function. So what are we going to have to do? We're going to have to differentiate, or we're going to have to integrate. Okay, we're going to have to integrate, and we're going to have to integrate twice. We're going to have to integrate acceleration once to get velocity, and then we're going to have to integrate velocity again to get to position. Okay, so here's how we might set this up. A of t is equal to negative 4 sine of 2t. All right, and now I want to integrate, don't hate. So I'm going to add my operator for integration, a nice slender integral sign, and then my differential on both sides. So again, just like we learned back in algebra a million years ago, what you do on one side of the equation, you got to do on the other side. So here we're doing the calculus operation of integration, and there we go. Okay, I call the left side. Integral of acceleration is going to be velocity. So that's going to be v of t on the left side. Okay, now the right side. I'm going to take that negative 4, basically just kind of pull it through, kind of constant multiple. Now I'm looking at the integral of sine of 2t. Okay, well, that is going to be negative cosine of 2t, but I'm not done. So it's negative cosine of 2t. Now I got to know, what do I do with that 2? Well, if I was taking the derivative, chain rule would tell me to multiply by the 2, but I'm integrating, so I'm going to divide by the 2. So I'm going to write it right there. Okay. Now I'm going to clean this up just a little bit because I'm not done with it. That's my velocity function. Whoa. Okay. What did I forget? Go ahead. I can hear it. I can hear it right now. You guys are calling me on it. I've just, this is basically kind of like a differential equation. I've integrated both sides. On my independent variable side, you got it. plus C. What was I thinking? Okay, good save. So now I'm looking at, okay, I've got a negative here, a negative here. It's going to cancel out. I'm going to have 4 over 2. That's going to be 2. And then cosine of 2t plus C. Okay, now, how do we get a value for C? Well, that's why they give us really 2 initial conditions. They give us a velocity at time 0 is 7, and then they also tell us a position at time 0 is 0. So we're going to use the velocity initial condition, v at 0 equals 7. So I'm just going to take that and say, hey, v at 0. Okay, so I'm going to replace all my t's that live in the trees with zeros. So v at 0 equals 7 is equal to 2 cosine of 2 times 0 plus C. So 7, okay, 2 times 0 is 0. Cosine of 0 is 1. So this is 2 times 1 is 2 plus C. Then I'm going to subtract 2. I'm going to get 5 is equal to C. Okay. I'm going to take this velocity equation, v of t. This is really similar to doing a differential equation, isn't it? So I got v of t is equal to 2 cosine 2t plus 5. And then we want to integrate again. Integrate both sides, dt. The integral of velocity is going to be position. Yay, that's what we're looking for. And now we're going to integrate. So I'm going to pull the 2 out. The integral of cosine is going to be sine of 2t. What do we do with the 2? We're going to divide by the 2. Plus, we're not done. What's the integral of 5 with respect to t? It is 5t. Okay. Plus c. Didn't forget this time. Okay, that crosses out. Now what I have to do is I have to take that other initial condition, x at 0 equals 0. X at 0 equals 0. So that equals sine 2 times 0 plus 5 times 0 plus c. Wow, so that's exciting. Looks like 0 is equal to c, which means our position function, x of t, is equal to sine of 2t plus 5t plus 0. Please be an answer, please be an answer, please be an answer. Sine of 2t plus 5t, bada boom. Moving on. Which of the following is a solution of the differential equation y double prime minus 4y equals 0? Okay, this one, a little tricky. What we might do is we might say, hey, they're giving us 4 possible particular solutions. Well, let's see if we can like take the derivative of these particular solutions and which one is going to get back to this. So I'm just going to start with this one. So I want to take ddx of both sides. So I'm going to get y prime is equal to, that's going to be 2e to the 2x. Okay. I want to take the derivative again because I'm looking to get y double prime. So I take the derivative of the left side. I get y double prime. Over here on this side, I'm going to get, this is kind of easy. It's going to be 4e to the 2x. Now I'm going to look at what I got. This says y double prime minus 4y equals 0. So let's see what we got. Y double prime, that's our 4e to the 2x, minus 4 times y. Well, what's y? Well, y in this one is e to the 2x. Hey, look at that. 4e to the 2x minus 4e to the 2x is 0. That checks. Hey, we caught a break. The first one we tested was the correct answer. Okay. Moving on. All right. Shown above, this one's a pretty common one. Shown above is a slope field for which of the following differential equations? Okay. So here, a couple ways we can go with this one. I'm looking at my first 2 options and I'm seeing that y in the denominator there. Well, if that's the case, when y is 0, I shouldn't see any along here when y is 0 on the x-axis. I shouldn't see any tangent lines, but I do see tangent lines and they're horizontal. So basically, that can't be A or B. Because if y was 0, the tangents would be undefined. Okay, I'd expect to see vertical tangent lines, or so that's not going to work. Now what I'm going to do is I'm going to look and say, hey, quadrant by quadrant. I'm looking here, and in the first quadrant, x is positive, y is positive. So if I look at this one, x times y, I'd expect a positive times a positive. I would expect to see right here in this quadrant tangent lines with positive slopes. They don't have positive slopes. They're all negative slopes. So I'm going to take that one. That's my answer. Okay. Okay. This one here, 86, it's a calculator problem. Let R be the region in the first quadrant bounded by the graphs of Y. I'm going to call this Y1. I'm going to call this Y2. As shown in the figure above, the region R is the base of a solid. For the solid, each cross-section perpendicular to the, I was hoping for a square. It's an isosceles right triangle with a leg in region R. Okay, the leg, so that's going to be 1/2 is my constant. It's the integral from 0 to 2. Now I just got to figure out, you know what, it's really not going to matter because actually, since I'm going to square this, so I'm just going to go y1 minus y2 squared dx. Now I've just got to put that in my calculator and off I go. Bring my calculator back up. I'm going to go ahead and put it in as y1 and y2. So y1 for cosine of pi x over 4. And then y2 is going to be the quantity x minus 2 squared. Okay. Now I'm going to go to my main screen. I'm going to put in my integral. So that's 0.5 times the definite integral from 0 to 2. And now I'm going to have quantity y1 minus y2 quantity squared dx. Please be an answer choice. Please be an answer choice. And it is 1.7745. Sweet. Okay, student attempts to solve the differential equation dy dx with the initial condition y equals 2, x equals 0. Steps of the student solution shown below. Which of the following steps does an error first appear? Okay, first step looks good. Separated the variable. Whoa, look at that. They integrated the left side. That's not natural log of the absolute value of that. So the error first occurred in step 2. Okay. All right, 29, the graphs of the function g and the line x. So this is g, and then this is the